Welcome back to machine learning. Today's video is going to cover math for machine learning. So I'm going to cover some concepts that you should already be familiar with and just review them a little bit, kind of refresh your memory. We will be using a lot of these concepts throughout the course, and as more material is needed and more review is needed, that will be provided throughout the semester. We're going to cover two main concepts as part of the math review: linear algebra and vector calculus, which are the two main things that we're going to be using in this class. For our linear algebra review, we're going to talk about matrix operations, the identity matrix, the inverse, transpose, dot product, and matrix norms. So for addition, it's just an element-wise operation. So we take each element of A and combine it with each element of B to get some matrix C. So we use corresponding elements. That's why it's called element-wise. And so we add 1 and 5, we get 6. 2 and 6, we get 8. 3 and 7, we get 10. And 4 and 8, we get 12. So now we have our matrix C. A and B must be the same size in order for them to be added together. If they're not, then you run into all sorts of issues. So if we start going, suddenly we get to the third element in the first row of A, and there is no corresponding element of B. So this operation is undefined. It's basically like if we were trying to add a cat with the number 5, we wouldn't even know what to do with that. Okay, they're like two different types. So this is the general form, right? I is usually the row and J is the column. Cij is given the value of Aij plus Bij. Addition is commutative, so that means you can move the terms around and still get the same result. Subtraction is very similar in that it's an element-wise operation. Instead of giving an example here, I just go straight for the general form. Cij equals Aij minus Bij. Not commutative, so we can't swap the terms around and get the same result. Before we go into matrix multiplication, we're going to do multiplication by a scalar. A scalar is just a single value like 5 or 3.2 or literally any other single value. And so you can multiply a scalar by a matrix, and all you do is you take that scalar and you pull it into all elements of the matrix. And so in this example, we would pull the 5 in and multiply it by each individual element of the matrix, and we would get the resulting matrix. This is the general form of that. It's the same thing. This should be very familiar to you, so I'm going kind of quickly. You're, of course, welcome to watch this video as many times as needed or to slow it down. Matrix multiplication is a little bit more complex, so before we do that, we're going to detour to the dot product. The dot product is called the inner product sometimes. I'll probably switch back and forth, but I'll most likely use dot product most of the time. But basically, you can take two vectors, and you take the dot product of those two vectors, and you get a scalar, okay? So here, let's run through an example first. If we take the dot product of these two, we take 1 times 3 and 2 times 4, and we add them together. And that's it. It's really, really simple operation, but it's very powerful. So the general form is like this, right? So you sum over all individual element-wise multiplications. In order to take the dot product between two vectors, v and u, they must be the same length. This is a very powerful tool. One of the things that we're going to use in this class is that the dot product between two vectors is 0 if and only if those two vectors are perpendicular or orthogonal. And so you can check to see if two vectors are orthogonal or perpendicular by checking to see if their dot product is 0. Here's an example. The vector v is 1, 1. The vector u is negative 1, 1. And we can see that v dot u is 0. And if you actually plot this, you see that that's true. Okay, back to multiplication. So if we have a matrix A and a matrix B and we want to multiply them to get some matrix C, we actually take dot products between the rows of A and the columns of B. Okay, so we take the dot product of the first row of A and the first column of B, and we put the result in the first row, first column of C. Okay, so that's what we get here. 1, 2 dotted with 1, 3 is 7. Okay, now we move over to the second column of B so that we can fill in the first row, second column of C. We get 10. Then we move on to the second row of A, and we start back over at the first column of B. We get 15. And then finally, we do the second row and the second column, and we get 22. A row of A must be the same length as a column of B. This makes sense because we're taking the dot product between rows of A and columns of B, so they must be the same length. Another way of saying this is that the number of rows in B must match the number of columns in A. So if we have some matrix A, which is R by C, rows by columns, and B, which is N by M, then N must equal C in order for us to multiply them, okay? So here's the more general form of this matrix multiplication. We see that Cij is equal to the dot product of the ith row of A and the jth column of B. Okay, so this notation is a little bit kind of Python-esque with the colon, but it basically means the whole row or the whole column. Okay. Now, once we know what multiplication is, division becomes a little bit easier, but first let's start with the inverse of a scalar. So a scalar, again, is just a number, remember, and the inverse of a scalar is just 1 over that number. So scalar division, A divided by B, is the same as A times the inverse of B. Okay, so that's what we're going to do with matrix multiplication. 10 divided by 5 equals 10 times 1 over 5, which is 2. So the inverse of a matrix is what we need to do matrix division. Okay, so A divided by B is A times 1 over B, which is A times the inverse of B. So what is a matrix inverse? Turns out the inverse of a matrix is actually very complicated, and there's all these crazy formulas, and I'm not going to make you memorize those. So here's the formula for a 2 by 2. This should be reasonably easy to remember. I may expect that you remember it, but generally speaking, I'm not going to ask you to take the inverse of a matrix very quickly. And I certainly won't ask you to take the inverse of a 3 by 3. So if you're taking the inverse of a 3 by 3 on some sort of quiz or exam, you're approaching the problem incorrectly. Here's an example of this inverse formula, just so you can see it in action. We can see that we have the matrix 1, 3, 1, 4, and it becomes 4, negative 3, negative 1, 1. In order to take the inverse of a matrix, it must be square. Now, what is the identity matrix? The identity matrix is like 1, but it's for matrices. So when you multiply a scalar by 1, you get the scalar back. When you multiply a matrix by the identity matrix, you get the same matrix back. So it's just 1s along the diagonal. It's an n by n matrix, and it's 1s along the diagonal. So the 2 by 2 looks like that. The 3 by 3 looks like that. What does the 2 by 3 look like? There is no 2 by 3 because the inverse matrix is always square. So the inverse of a matrix is defined like this, right? A times B equals B times A equals I. So if A and B are inverses, I should be able to multiply them together and get the identity matrix. Like so. So I remember I took the inverse of this matrix. Now if I multiply them together, I do get the identity matrix. So that's how I can say, okay, how do I know if these two matrices are inverses? Well, I can just multiply them together and I'll get the identity matrix. So that's a useful little tool. So matrix division, all the way back to that, right? We just multiply by the inverse. So first we have to take the inverse of the matrix. Once we do that, we just multiply as per normal. The transpose of a matrix is very simple. You simply take the rows and turn them into columns. And so the transpose of 1, 2, 3, 4 is 1, 3, 2, 4. And more generally, it's like this. So Aij becomes Aji. The norm of a matrix is very useful. It gives you some sense of length. There's a lot of different norms. One of the ones we're going to focus on in this class is the L2 norm. It's also called the Euclidean norm. It's displayed like this with the 2 bars on the side, and sometimes there's a little 2 at the bottom. Sometimes it's not there. The 2 bars is enough to let you know that that's the L2 norm. So all that is the square root of the sum of the elements squared. So it's basically the Euclidean length of that vector. So if we have a vector 3, 4, we take the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. It's the generalized form of the Pythagorean theorem, okay? So the vector v, if it's 3, 4, looks like this. And so you take each element 3 and then 4 to get the distance and the length, okay? The L1 norm is another common norm. This one is denoted by just single bars on the outside. And this is just the sum of absolute values, okay? So if we take our same vector 3, 4, we see that the L1 norm is actually 7, not 5. And this norm is sometimes referred to as the Manhattan or taxicab distance, and that's just because the length of the vector, the L1 norm of a vector, is the distance it would take taking axis parallel lines. So you're traveling along city blocks basically, and you can only go right or up in this situation. So you can't go directly there, you can't walk directly there, you have to drive on the roads, and the roads are set up in a grid like they are in Manhattan, okay? So if you count all these orange lines here, you'll see that you have 1, 2, 3, 4, 5, 6, 7 of them. So you take 7 unit steps to get there. That's it for the linear algebra portion of this video. We covered matrix operations, the identity matrix, the inverse, transpose, dot product, and the norm. Now we're going to move on to vector calculus. The 2 most important things that you need to know are derivatives and gradients. So I think we all kind of forgot about derivatives. It's probably been a while since you've had to do anything with them. So I just kind of want to refresh your memory. Remember that use the chain rule for basically everything. So the derivative of x is 1. The derivative of x squared is you pull the 2 out in front, right? Like that. The derivative for this, we're going to pull that 4 out, right? Multiply it by the 3, and then reduce the exponent by 1. So then we'll get 12x cubed plus 2. So don't forget that second term needs to have its derivative taken as well. The notation for derivatives gets a little bit messy when we start talking about 5th and 6th and 7th derivatives, because it's really just this little asterisk. And as we add more of those, it gets a little bit more difficult to deal with. So instead, people use this lower bullet notation where we take the derivative once, df dx, take the derivative twice, d squared f dx squared, and so on, okay? So then what we want to move on to is partial derivatives. If we take the derivative of a function and it has multiple variables, you can take the derivative with respect to each of those variables. So if we have a function f of x, y, and we want to take the derivative, we need both of them, right? So what does it mean to take the derivative? Are we taking it with respect to x or with respect to y? So if you take the derivative with respect to x and y, then you can describe the derivative of this function as the gradient, and you can put those two together in a vector, which we'll see in a second, okay? But the derivative of this function with respect to x is 1, and with respect to y is 0, because there is no y term, so you're taking the derivative of a constant, and the derivative of a constant is 0. Moving on to this function, another simple function. The partial with respect to x is 1, and the partial with respect to y is also 1 in this case, because there actually is a y term. The next one is a little more complicated. X is multiplied by y. But remember, when you're taking the derivative with respect to x, y becomes a constant, and the derivative with respect to y, x becomes a constant. So it's just as if you had 5x here. The derivative would be 5, right? But instead, it's y. And so the partial with respect to x is y, and the partial with respect to y is x. Now for a more complicated example, just to get the derivative blood flowing. If we take the partial with respect to x, we have to take that exponent down to the front, so then we get 2 times 2 is 4xy. The second term doesn't have any x's in it, and so it's a constant, so it goes away. The derivative with respect to y treats the 2x squared as a constant, and so it stays, and then we pull the exponent down in the second term, and we get 9y squared. So the notation, again, is the same as that kind of fancier notation, and allows us the freedom to take derivatives with respect to x, then y, then x, and so on, if need be. as you can see in the bottom row. The gradient is just a multivariable generalization of the derivative. The derivative gives you a scalar output, one value. The gradient gives you a vector output. So if we take this function, f, and we take the derivative with respect to x and with respect to y, we get these two different values. And then we can actually take those two values and put them into a vector, and then we have the gradient. And that's it. That's all the gradient is. It's just, hey, take all these partial derivatives and squish them together in a vector, and then you can describe the derivative of this function, which has multiple variables, in terms of one thing, one vector. Then you can plug numbers in. So we can take the gradient at a particular point, in this case 1, 1, and we'll get the value 3, 3. So that means that the partial derivative with respect to x is 3, and the partial derivative with respect to y is also 3 at this point. Here's another example. You have to take each partial, right? Take each partial derivative, and then you squish them together into a vector, and that's it. So for vector calculus, derivatives and gradients are the only thing that you really need to be comfortable with at this point. If you need more review than this, you need to seek that review. So linear algebra and vector calculus are going to be some of the main points that we cover in class. As more is needed, I will provide more materials. The next topic will be decision trees, so go check out that video before our next week.